For today's experiment, we are going for verification of port characteristics of directional coupler. And you know that directional coupler, so directional coupler contain how many ports? As we know that directional coupler contain a port device. So when we go for directional coupler or a diagram of a directional coupler, so it contain a four-port device. So when we go for S parameter matrix of directional coupler, so it is a 4 by 4 S parameter matrix you are getting for a directional coupler. So this is port number one of a directional coupler from which we give the input. Then port number two, you can obtain output from port number two. And port number three is terminated. Here port number three is terminated using a match termination, and port number four you can get an output. So here as shown in this diagram in directional coupler, two particular waveguides or two rectangular waveguides, they are coupled with each other, and there are two tiny holes present, and they are separated by distance which is equal to lambda g by 4, that is guided wavelength divided by 4. And wave from the port number 1, it is given to port number 2, and it is from the main waveguide. But these waveforms from the main waveguide, they are coupled with the auxiliary waveguide also. So see here, this second one is an auxiliary waveguide which having port number 3 and port number 4. So waveform from the port number 1, that is from main waveguide, they are coupled with the auxiliary waveguide by using two tiny holes that is present um, in between this auxiliary and main waveguide, and you can obtain some output from the port number 4 also. So it is a directional coupler, means you can provide input from port number 1, and that can be obtained from port number 2 as well as port number 4 also, where in this case port number 3 is terminated. So here we have to go for finding port characteristics of directional coupler, and these characteristics can be found using some parameters. So normal micro test bench setup we required for performing this directional coupler experiment. And there are parameters. So there are parameters like there is insertion loss. So you can find insertion loss in a directional coupler using formula like it is 20 log to the base 10 V1 upon V2, and it is measured in decibel. So V1 is voltage at the output without directional coupler, and V2 is voltage at output with directional coupler, means V2 is voltage after insertion of directional coupler. Similarly, there is parameter called as coupling coefficient. So coupling coefficient means it indicates how much power is coupled to that particular directional coupler. So it is 20 log to the base 10. Again, it is V1 upon V2. And again, you find out this directivity of a directional coupler. So directivity of directional coupler, it can be given using formula like 20 log to the base 10 upon V3 upon V4. Here V3 is what we can say that input from output from port number 3, and V4 is output from port number 4. But in practice, this V3 get terminated. So we have to modify these certain formulas, and there are some formulas like you can calculate insertion loss using 20 log to the base 10 V1 upon V2. V1 is input before insertion of directional coupler, and V2 is voltage after insertion of directional coupler. Similarly, you can find out the coupling factor. So it is 20 log to the base 10 V1 upon V4. So here V1 is input at port number 1, and V4 is output at port number 4. So we know that there are some output is coupled from main waveguide to auxiliary waveguide, and it is came out from port number 4. Similarly, you can calculate directivity by using formula. It is 20 log to the base 10 V14 upon V24. So here V14 indicate input at port number 1, output at port number 4, and V24 indicate input at port number 2 and output at port number 4. So for calculating directivity, you have to calculate, or you have to attach directional coupler in reverse order. And then you can calculate VSWR by using slotted section, or by moving V long slotted section, you can find out this V max and V minimum. for main line as well as for auxiliary line, or for auxiliary waveguide and main waveguide. And when you know the Vmax and V minimum, you can calculate VSWR by taking ratio of them. And similarly, you can calculate isolation. So isolation is addition of directivity, which you have calculated by using this formula, plus coupling factor, that is calculated using this particular formula. So all these are in decibel because we are using here 20 log. When we go for particular these parameters, so directional coupler and its characteristics can be found by using parameters like insertion loss, coupling factor, then directivity and isolation. So I had prepared all these particular parameter, or there is a video I will show you here for this how to find out these parameters. Good afternoon, students. Today we have to perform experiments on multi-hole directional coupler. So see here, this is actual photo of an multi-hole directional coupler. Actually, this directional coupler is a 4-port device, means it having port number 1, port number 2, port number 3 is terminated using match termination. It should be shown here, and then there is a port number 4. And when we see the diagram or a physical structure of multi-hole directional coupler, then it is made up of two waveguide. One is called as main waveguide and another one is the auxiliary waveguide. So this multi-hole directional coupler contains two tiny holes, and they are separated by a distance equal to lambda by 4. And input from port number 1, suppose we consider here input is given at port number 1, then you are getting output from port number 2 as well as port number 4, because here waveforms from this main waveguide is coupled to the auxiliary waveguide by using that two tiny holes, and they are passing from main waveguide to auxiliary waveguide. So we are having some output at port number 4. So this is a multi-hole directional coupler, and in this experiment we have to find out port characteristics of this multi-hole directional coupler. So there are certain parameters regarding an directional coupler, like there is a VSWR for main arm as well as for auxiliary arm. Then there is a isolation as well as there is a coupling factor and directivity. So you can find all these parameters with the help of this experiment. For performing this experiment, again we required a microwave test bench setup, which required a klystron power supply, then klystron tube, and a cooling fan as a heat sink for that particular klystron tube, isolator, then direct reading frequency meter, slotted section, and output of slotted section is connected to a detector mount which contain a Schottky barrier diode which detects microwave signal, and then it is taken out from wire between a particular detector mount and CRO. So you have observed waveform on CRO. First thing is that what we have to do, we have to energize the klystron, and for energizing the klystron you have to go for switching on this klystron power supply first. And when you switch on this klystron power supply, then this display select switch is on voltage, and first you have to select the beam voltage. So you have to vary this beam voltage now until it is equal to 250 volt. So now this beam voltage is nearly equal to 250 milliampere. Sorry, it is in volt. Then after that we have to check the beam current. So for checking the beam current, you have to switch this knob to current, and then it indicates the beam current. And this beam current is having value equal to 17 milliampere. This value should not be greater than 25. If it is greater than 25 milliampere, then it may be possible that the klystron get burned due to excessive heat, as it contains a filament. And after that you have to go for again changing this switch to the reflect. Okay, so now the switch position is at repeller voltage. Then what you have to do, you have to move the repeller voltage until you get the first mode on klystron. And for observing mode, you have to go to the CRO. And here I am moving that repeller voltage knob, and that should be movement until I get a first mode of klystron. So at a voltage equal to 197 volt, I am getting a first mode of klystron, and say this may be a voltage V1, and I have to measure this voltage. So I will check this Y position of this voltage, and here it is equal to 2 multiplied by, it is 0.5 volt. So it is 2 multiplied by 0.5, so it is equal to 1 volt. So you are getting output of this particular first mode of klystron, and your here output should be, it is 2 multiplied by 0.5, so which is equal to 1 volt. So say it should be V1, and you have to calculate the insertion loss. We have to insert a directional coupler in between this slotted section and detector mount, and then you have to find out V2, so that is voltage after insertion. So there are two voltages, like there is V1, so V1 is voltage before insertion of directional coupler, and V2 is voltage after insertion of directional coupler. You are getting value of V1, so that is equal to 1 volt, but we want to find out V2, so that is we need to connect an directional coupler in between this slotted section and detector mount. Then you can obtain V2 by connecting detector mount to the port 2. But everyone listen here, this directional coupler contain port 4 also. So for finding V2, you have to put this port 4 terminated using match termination. So when you know the value of V1 and V2, you can find out insertion loss, like it is 20 log to the base 10 in bracket V1 upon V2. Okay, so now as shown here, an directional coupler is inserted in between slotted section and detector mount. So port number 1 of directional coupler is connected to this slotted section, whereas port number 2 is connected to a detector mount, and port number 4 is terminated using match termination, whereas this port number 3 is already terminated. So this is set up for finding V2. We have to go for finding insertion loss, and insertion loss having formula like it is equal to 20 log to the base 10 V1 upon V2. So V1 is voltage at CRO without DC directional coupler, and V2 is voltage at CRO with directional coupler. So we are getting V1 as 1 volt, but we now want to find out value of V2. So here output is connected to port number 2, and you are getting directly this value of V2. So this V2 is nearly equal to 0.6 multiplied by 0.5, so it is 0.3 volt. So you are getting V1 as a 1 volt, but V2 is equal to 0.3 volt. And when you put this value of V1 and V2 in this above formula, then you are getting insertion loss, so which is in decibel, because your formula is in 20 log to the base 10. So listen here, now using this same setup we can calculate the VSWR here. Here in this setup, port number 1 is connected to slotted section, output is connected to port number 2, and port number 3 is terminated as well as port number 4 is terminated. So using this setup we can find out the VSWR. For finding VSWR, what we have to do, we have to move the wheel on this slotted section. So whenever we move this wheel on particular left side, then as we are moving, this particular amplitude is increasing, again it is increasing, again it is increasing, again it should be increasing, still it is increasing. So we will go for adjusting this channel 1's setup, and again we are going for this increasing voltage, but after this point it start decreasing, so we will go for a reading at this point, and this particular value is equal to so this is equal to 1.6 multiplied by 1 volt, so it is equal to 1.6 volt. So you are getting V max as for main line, it is equal to 1.6 multiplied by 1, which is equal to 1.6 volt. So similarly you can find out V minimum, and for finding V minimum again you have to move this wheel on slotted section until you are getting minimum value. So this is minimum value we are getting, and I have to adjust this Y position here. So this is nearly equal to 0.2. So it is 0.2 multiplied by 1 volt, so it is 0.2 volt. So here you are getting V max as a 1.6 volt and V minimum as a 0.2 volt, and by taking ratio of this V max and V minimum you can find out VSWR easily. So this is set up when we go for finding particular VSWR for this main line. Okay, so now as a second parameter we have to calculate here the coupling factor, so which having formula like it is equal to 20 log to the base 10 upon V1 upon V4, and we already calculated V1, so that is voltage at CRO without directional coupler or voltage at port number 1, and that is equal to 1 volt, but we want to find out V4. So for finding V4 this is set up. So for finding V4 output is connected to port number 4, and output from port number 4 is connected to a CRO, whereas in this case this port number 2 is terminated using match termination, so directly you are getting value of V4. So here when we observe this value of V4, so it is nearly equal to 0.6 multiplied by 0.2. So this V4 is 0.6 multiplied by 0.2 volt, so it is 0.12 volt. So this is output you are getting as a V4, and by putting this value of V1 and V4 you can easily calculate this coupling factor. Similarly you want to find out this directivity. Directivity is another parameter, and for finding directivity the formula is D equal to 20 log to the base 10 V14 upon V24. So here V14 is means input at port number 1 and output at port number 4. So same position it should be present over here, like input is at port number 1 and output you are getting from port number 4, but here port number 2 is terminated. So this is nearly equal to V4, so that is nothing but it is equal to V14, which is equal to 0.12 volt. So this is output of V14 you are getting. Similarly for calculating directivity you have to need finding V24. So V24 means exactly reverse position of this, means you have to reverse the directional coupler, means input at port number 2 and output at port number 4, and in that case port number 1 is terminated, so you can obtain the V24. We will see later how to go for that V24 and what is the value of that. And finally you can calculate isolation. So isolation is addition of this directivity you are getting and coupling factor in decibels. So by addition of this both term, directivity and coupling factor, you can get the isolation. And now in this particular setup, you can find out VSWR for auxiliary line. Means now input is at port number 1 and output is at auxiliary line, means port number 4. So you can find out this VSWR for auxiliary line now. So for finding that auxiliary line VSWR, again we have to move the wheel on slotted section for finding Vmax and Vminimum. So we are going for finding Vmax. As I am moving the wheel on slotted section, this is increasing, amplitude get increasing, again it is increasing, but after this point it start decreasing. So we have to find out that point where it is higher value. So and I have to adjust the Y position here again on CRO. So that is equal to 1 plus, say it should be 4. So it is 1.4 multiplied by 0.2 volt. So it is okay. So we had finded the Vmax here. So what we have to find is Vminimum. For finding Vminimum, we have to rotate the wheel on this slotted section again on left side, and we have to rotate until you are getting a minimum waveform here. So this is minimum waveform we are getting. So we have to adjust the position of this Y position on CRO. So it should be nearly equal to 0.2 multiplied by 0.2 volt. So here Vminimum is 0.2 multiplied by 0.2 volt. So you are getting this Vminimum and Vmax, and by taking ratio of this Vmax and Vminimum, you can find out VSWR. So here what we have to find remaining is V24. So V24 means output at port number 4, where input at port number 2. So for finding V24, what we have to do, we have to just reverse the directional coupler, and then you are getting output at port number 4. So that is V24. So for this directional coupler experiment, these parameters we had found. So that is insertion loss, coupling factor, directivity, isolation, and VSWR. So thank you for watching.